Hello, I'm Kevin Craig. I have created 12 modules on electronics and measurement for mechatronics. Modern engineering practice demands that engineers model, analyze, and predict before they measure. What is mechatronics? The diagram you see I created in 1995 as a professor at Rensselaer Polytechnic Institute. It is used now throughout the world to represent the field known as mechatronics. Mechatronics is multidisciplinary systems engineering. It is the synergistic integration of physical systems, electronics, controls, and computers through the design process, from the very start of the design process. These modules present the fundamentals of electronics and measurement for mechatronics. This module is on the H-bridge. Here is a diagram of a H-bridge. The H-bridge consists of 4 transistors. Here I show power MOSFETs, metal oxide semiconductor field effect transistor. The MOSFET has a gate, a drain, and a source. You learned about the MOSFET in a previous module. Internal to the MOSFET is a flyback diode for back EMF suppression. Here we use the Schottky diode. You learned about this in the module on diodes. The 4 transistors are arranged as shown between a voltage source and ground. This resistor is called the sampling resistor. It can be used to measure the current flowing through the motor by sampling the voltage across that resistor. The motor is attached as shown in the crossbar of the H. Here is a blown up picture of the N-channel power MOSFET. The input to the gate is a PWM signal, pulse width modulation, which you learned about also in a previous module. We show the flyback diodes, the Schottky diode, and the 3 pins for the MOSFET: gate, drain, source. Please note that on the actual hardware, the pins are numbered 1, 2, 3 from left to right: gate, drain, source. On the schematic diagram, the pins are gate 1, drain 2, source 3. Please don't mix these up. Rather than using 4 individual transistors to create the H-bridge, we can use a semiconductor chip like the L298 dual full bridge driver. It consists of 2 H-bridges, one on the left, one on the right. Each H-bridge has 4 transistors. No diodes are included. In addition, there are logic gates for the L298 operation. Each H-bridge has its own sense resistor for sensing current. H-bridge operation. For DC electric motors, power device configuration called an H-bridge is used to control the direction and magnitude of the voltage applied to the load. The H-bridge consists of 4 electronic power components arranged in an H shape in which 2 or none of the power devices are turned on simultaneously. A typical technique to control the power components is via a PWM, pulse width modulation, signal. A PWM signal has a constant frequency called the carrier frequency. Although the frequency of a PWM signal is constant, The width of the pulses, the duty cycle, varies to obtain the desired voltage to be applied to the load. Here we see the diagram of the H-bridge with the motor. Our 4 power MOSFET transistors, the pulse width modulated signal to the gate of each transistor, the Schottky diode for back EMF suppression, the flyback diode, the voltage source, the sensing resistor, and of course ground. The H-bridge can be in one of the 4 states: coasting, moving forward, moving backward, or braking. In the coasting mode, all 4 devices are turned off, and since no energy is applied to the motor, it will coast. In the forward direction, 2 power components are turned on, one connected to the power supply and one connected to ground. In reverse direction, only the opposite power components are turned on, supplying voltage in the opposite direction and allowing the motor to reverse direction. In braking, only the 2 devices connected to ground are turned on. This allows the energy of the motor to quickly dissipate, which will take the motor to a stop. The 4 diodes shown in anti-parallel to the transistors are for back EMF current decay when all transistors are turned off. These diodes protect the transistors from the voltage spike on the motor leads due to the back EMF when all 4 transistors are turned off. This could yield excessive voltage on the transistor terminals and potentially damage them. They must be sized to a current higher than the motor current and for the lowest forward voltage to reduce junction temperature and the time to dissipate the motor energy. Here we see the H-bridge in the coast mode. All 4 transistors are off. Here is the H-bridge in the forward mode. We see that the upper left transistor is on, the lower right transistor is on. The other 2 transistors are off. Current flows as shown through the upper left transistor, through the motor, through the lower right transistor, through the sampling resistor to ground. Here is the H-bridge in the reverse direction. Now, the upper right transistor and the lower left transistor are turned on, and current flows as shown from the power supply through the upper right transistor, through the motor, through the lower left transistor, through the sampling resistor to ground. To break the motor, the 2 transistors in the upper portion of the H-bridge are turned off, and the 2 transistors in the bottom portion of the H-bridge are turned on. And this allows the motor to brake. When we have a transition from on to off, as we do, for example, when we go from the forward direction to reverse direction or braking, the upper left transistor goes from the on state to the off state, and the lower right transistor goes from the on state to the off state. When they are on, the current flows as shown by the solid red line from the supply through the upper left transistor, through the motor, through the lower right transistor, through the sampling resistor to ground. When the transistors are turned off, the energy that's present in the magnetic field of the motor windings dissipates by allowing the current to flow as shown by the dashed blue lines. And the current flows in the direction of the Schottky diodes. So the current flows as shown here through the Schottky diode of the lower left transistor, back through the motor, through the Schottky diode of the upper right transistor, and back to the power supply. This is how we prevent any voltage spikes from occurring and damaging the transistors. The H-bridge is used to control brushed DC motors, brushless DC motors, and step motors, the three main motors in mechatronic applications. This concludes the module on the H-bridge. Thank you for your attention.